In this video, I'm going to talk about how to calculate the acceleration due to gravity on different planets using Newton's universal law of gravitation. So let's start with a simple example. Let's go with Earth. So with Earth, we know the value to be, for the acceleration due to gravity, to be negative 9.8 meters per second squared, okay? And we use that value in our problem. So how does this value obtain using Newton's universal law of gravitation? Because once we do this for Earth, then we can do it for another planet or celestial body. So let's take a look here. If I take a look at Newton's universal law, it's F is equal to capital G, the gravitational constant, times the mass of the Earth, times the mass of a little object here, I'll call that little m, over r squared, the distance from the center of the planet to the center of the object. So for the Earth, this number is 6.67 times 10 to the minus 11th, that's capital G, the universal constant, times the mass of the Earth, which is 5.97, times 10 to the 24th, times the mass of the object, and I'm going to use a mass of 90 kilograms here. So 90 kilograms for that other object, over the distance squared. So let's see, the radius of the Earth, since we're on the surface of the Earth, I'm going to say the radius of the Earth is 6.37 times 10 to the 6 meters, 6 squared, which gives us a value of 890 newtons. Now that's the force that's acting on it. So that's the force acting on it, which is still mg, and that's 890. So g, if I have a 90 kilogram object, if I solve for g here, it's 890 divided by the value of 90, and let's see what I get here. Is 9.88 meters per second squared. Okay, so that's how we arrive at that number using Newton's universal gravitational law. So if I went to a different object, let's say I'll go to the sun. So it's not drawn to scale. This thing is really huge, the sun. But if I were to find the force due to the sun, it'd be 6.67 times 10 to the minus 11th. Now the mass of the sun is huge. It's actually 1.99 times 10 to the 30th. So that's 6 more decimal points times the same mass of 90. If I put a 90 kilogram object on the surface of the sun, assuming it didn't disintegrate due to the heat, and the radius of the sun is 6.96 times 10 to the 8th meters squared. And that force, if you calculate the force on the surface, is 24881.09 newtons. Okay, this is only 890 newtons here, so it's a lot bigger. So what would be the acceleration due to gravity on the surface of the sun, or near the surface of the sun? Well, again, it's mg, except that number is not 890, it's 24881. And so the gravitational acceleration on that planet, or excuse me, on the sun, would be 24881 divided by the 90 kilogram object, divided by mass, solving for g here, divided by mass, is going to be 276.46 meters per second squared. So that is an entirely different acceleration. Huge. This is the magnitude. We know it points down, so technically, comparing here, it's g is equal to, because it points down, negative acceleration, negative 276 times 46 meters per second squared. And so that's the acceleration to the sun. And just a quick little calculation shows that it is about 27 times the acceleration due to gravity on Earth, 27 Gs, 27.9, actually almost 28 Gs. If you divide this by that, it's 28 times it. At any rate, you can use Newton's universal law of gravitation to find the force. It's still equal to mg. When you divide by m, it's in this case 9.8, which you normally get. And then if you did it on a different celestial body here, like the sun, I used the numbers for the sun here, I got an entirely different force. Divide by the mass, the 90 kilogram object, and I get 276.46 meters per second squared. So those are the calculations you'll do to calculate the new g for either energy or kinematics problems or force problems.